Weather radar. Figure, weather radar on the Western Cape in Stadlandet. Behind the white dome hides a rotating satellite dish. Rain, later rain showers. The weather forecast in Western Norway passes judgment on another summer. I, the little boy, sit alone and listen to the gloomy message that comes out on the AM medium wave of my aunt's orange transistor radio. The adults lie upstairs and rest. I hoped that we were just unlucky here in the West and that it would soon be sunny. When I became a student, I took a basic course in meteorology. There I learned that we were doomed to perpetual repetition of sweeping low-pressure fronts from the west. They first give a warm front with drizzle, then a cold front with rain showers. I went into a mild depression that has hardly relieved. I'm going to ride my bike home from work. I open Year, a fantastic service from NRK and the Meteorological Institute. I open the map that shows the rain showers journey as blue stripes over the map. Where it is dark blue, it rains a lot. I time my journey in a time slot between 2 showers to get home dry. In Norway, we have 9 weather radars in a nationwide network. They are located along the coast or high in the terrain so that they can observe large areas. Radar was developed before and during World War II. The purpose was to detect the enemy. A radar, Figure 1, emits an electromagnetic wave in a short strong pulse and then enters listening mode. Figure 1. Schematic diagram of a classic radar. The magnetron provides energy for a short pulse that is sent out by the antenna. Then you listen, and the echo is sent down into a mixer and detector before it is displayed on the screen. The emitted pulse hits some object that reflects some of the energy back as an echo. This echo can then be processed to find out what one sees. To get better resolution, one experiment during the war was to reduce the wavelength of the pulse to send out the energy in a narrower beam that could be swept across the sky with a movable antenna. Instead of seeing Fritz in his bomber, the entire echo was filled with echoes from precipitation. The weather radar was born, and the rest of the war was used to research radar echoes from precipitation and how to filter out what they saw as noise. After the war, some of these scientists became unemployed and began to look at how radar technology could be used for peaceful purposes. Now, you find weather radars in the nose on all commercial flights and on the ground. They are scattered evenly all over the Earth as an important element in weather forecasting. In addition, there is a scaled-down version of the energy source of the radar pulse, microwave, in all microwave ovens. Important for the development of weather radar was the so-called Stormy Weather Group in Canada led by J.S. Marshall. He and doctoral student Walter Palmer found out how the droplet size in rain is distributed as a function of the rain intensity measured in mm/h. In short, the more intense the rain, the bigger the drops. With this knowledge, one could find the connection between radar echo and the intensity of rain, the so-called ZR relationship. When radar waves are on the order of 10 times larger than the raindrops, you get reflected back echoes from the rain. If you use shorter radar waves, which could be tempting to get a better resolution, the echo is greatly attenuated and useless. Rain radars primarily use 10 cm S-band and 5 cm C-band wavelengths as the size of raindrops varies between 8 to 0 mm in diameter. The problem with precipitation is that it comes in so many forms: rain, snow, sleet, and hail. Sleet, for example, reflects radar waves much better than rain. If we assume that it is raining and measure when it is instead sleeting, then the ZR relationship will give too much intensity to the precipitation. By combining the radar pulse with 2 radio waves with different polarization where the waves are normally on top of each other, you can determine the type of precipitation and look further into the shower to show the internal structure. When raindrops become large in intense rain, they become oval in shape due to air resistance and wind. Radar with 2 polarizations then gives a different echo for the 2 polarizations in heavy rain, and then you know that there is no sleet or hail. To find out how fast the precipitation moves, one uses the Doppler effect. As something comes toward you, the wavelength becomes shorter, and as it moves away from you, it becomes longer. This change in wavelength can be measured by radar. From the weather radar comes a continuous stream of data that meteorologists can use in different ways. We have all been happy with the map on year, but there is much more. One can accumulate precipitation data for a given area over a given time and thus obtain hydrological data. Since you can swipe the antenna and look into the rainstorms, you can also visualize them in 3 dimensions, as in Figure 2, and see what they contain in terms of precipitation intensities and types. Figure 2. A 3-dimensional presentation of a rainstorm. In the cardinal plane is projected what threatens from above. On the way home, I bicycle past several base stations for mobile telephony. Most of them are fed by microwave radio links. These radio links are, in the same way as the radars during the war, vulnerable to precipitation attenuation. Maybe you could use data from them as a network of local weather radars so you could know what weather is coming around the next turn?